In this video, we will look at objects of limit state design. Limit state design, which is also known as LSD, limit state design, call it LSD, or we call it load or resistance factor design, load and resistance factor design, LSD, LR, that is load resistance factor design, LRFD. Is a design method used in structural engineering. A limit state is defined. Limit state is defined as a condition of a structure beyond which it no longer fulfills its intended purpose of design, or it does not fulfill the relevant design criteria. And when we're talking about design criteria, we're talking about fitness for purpose. Fitness for purpose. One, we look at safety and reliability. We look at durability of the structure. We look at economy. We look at the fifth condition or criteria, which is external appearance. Then we look at the sixth one. We're talking about users' comfort. And then we also talk about the robustness of the structure. Talk about robustness. So these are the criteria for limit state design. Fitness for purpose. The structure should be fit to perform the intended purpose of design. Safety conditions. It should be safe and reliable. Durability should also last. Economy will consider good value for money. Then we'll consider its appearance. It should be free from cracks and other defects. Then under user's comfort, we're considering it should also not discomfort or make the users. It should be fit for the users to stay there without being alarmed on the structure likely to fail or collapse. So limit state criteria require the structure to satisfy two principal criteria. We're looking at under criteria for structural design or limit state. The structure should fulfill ultimate limit state. Two criteria needed for limit state design. Criteria include: one, ultimate, it should fulfill or satisfy the ultimate limit state. Ultimate limit state, which we'll call the ULS. Then the second criteria is the serviceability limit state. Serviceability limit state. This one is SLS. This is the second criteria. So any design process involves a number of assumptions. The loads to which a structure will be subjected must be estimated. We're talking about the loads to be estimated. Then we're talking about sizes of the members. So based on criteria, any design process involves a number of assumptions. The load, under the assumptions, one, the load to which the structure will be subjected must be estimated. Estimation of loads, estimation. Then we are considering sizes of members to be checked, or to check must be chosen. Talking about sizes of members. Then the next thing we have to look at, the design criteria. Design criteria. So these are the three things we have to consider. Then we look at the next thing we look at under serviceability limit state. Under serviceability limit state, we have to consider three conditions. We consider limit state of deflection, the limit state of deflection. One, we consider limit state of cracking. Two, we consider limit state of vibration. Limit state of vibration. So these are three serviceability limit states we need to consider. In addition to the ultimate limit state check, which we've mentioned above, the serviceability limit state, computation check, and the serviceability limit state, the computation check must be performed. So we have to also carry out some checks. As for the ultimate limit state, we are not under the ultimate limit state checks and the serviceability limit state. As for the ultimate limit state, the serviceability limit state is not a physical situation, but rather a computational check. So the load factor resistance should also, the load and the resistance factors are determined using the statistics and pre-selected probability of failure. Variability in the quality of the construction, consistency of the constructional materials are also accounted for in factoring the loads. So the next thing we also look at are the code of practice. Look at the code of practice. Code of practice. Example, we have BS 8110. Previously we have CP 110. We have CP 114. We have CP 115. We have CP 116. Presently, the Eurocode 2 supersedes the BS 8110. So the BS 8110 is a withdrawn British standard for the design and construction of reinforced and pre-stressed concrete structures. It is based on the limit state design principle. So in the year 2004, BS 8110 was replaced by this very one. BS 8110 was replaced by the Eurocode 2, which is known as EN 1992 or Eurocode 2. You can also call it Eurocode 2 or EC2. So from there, the next thing we also look at, is mixed proportion, concrete mixed proportion. And we know that in preparing the concrete for reinforced concrete design, we are considering the components of the concrete such as cement, talking about coarse aggregates, and fine aggregates. So fine aggregates, we're talking about ratio coarse aggregates. So we're talking about C ratio FA ratio CA. So the components of the reinforced concrete, or for reinforced concrete design, we also include another component, the fourth one, known as plus the reinforcement bar. So the four components are these: the cement, the fine aggregates, the coarse aggregate, and the reinforcement bar. So, but in structural design, we consider the design of structures like, there's types of structures under structural design. Design structures in concrete or reinforced concrete. Reinforced concrete. 2, we consider steel. We design structure in steel. And 3, we talk about timber. We design structure or structures in timber. So from there, we move to another topic known as the characteristic strength. Characteristic strength. Strength of a material. Strength of materials. Be it concrete, be it steel, be it timber. The characteristic strength of the material is defined as the strength below which 20 test results are likely to fail. The characteristic strength of a material is defined as the strength below which 20 test results are likely to fall. Results are likely to fall, and this strength denoted by FK, F subscript K, or F subscript K prime, is that value below which not more than 5% of the test results may be expected to fall. So after crushing of the concrete or the concrete cubes at 28 days strength, we'll crush at 28, we look at 14, 7, 14, 21, 28, or 28 days is where we record at these days, or this particular day, the concrete is expected to have reached over 50%, gain over 50% of its strength. So at 28 days, we plot the strength, and this forms a bell-shaped graph. We obtain a distribution in this form, where this is the frequency, and we'll have the strength. So we'll have this. So if we have 5%, we expect that 5% of the test results should fall, not where we have at least not more than 5% of the test is expected to fall on this distribution we have here. So we term this as the characteristic strength of a material. So based on characteristic strength, which is FC, we have two grades. One for concrete, grade of concrete, which is FCU grade. We have grade 25, C25, we have C30, we have C35, in Newton per millimeter square for grade of steel. which is FY grade. We have the high yield steel and the mild steel. So we have high yield and the mild steel. High yield steel. This one is 460 Newton per millimeter square. We have the mild steel. This one is 250 Newton per millimeter square. So these are the grades of concrete and steel materials we have. Then the value of the characteristic strength is defined. For the characteristic strength, we define the value as here. This should be FK, not FC. So the value of the characteristic strength is given by the main strength, which is F main, Fm, subscript M, minus the 1.64 standard deviation, where we have the 1.64. This is for 1 in 20 tests, result falling below Fx, 1 in 20 test results falling below Fx. Then X, which we have here, this is standard deviation. Standard deviation. Why we call this the mean strength. Mean strength of the material, or mean strength from the test results. The test results. So the characteristic strength of concrete Fx, or this Fx, is the cubic strength of concrete at 28 days. Strength at 28 days. Then that of steel is the yield strength of reinforced steel, which is Fy at yield for steel. For steel is at yield. Then for the material selection at any particular time, we consider that it should not be more than 5%, shouldn't fall beyond 5%. Then other type of loads, the load for material selection at a particular is such that in the practice the actual strength is to be higher than the one you selected. Next, we look at type of loads. Load types, and we consider the dead load. The three type of loads we consider: 1, 2, 3. We talk about the dead load, which we denote by GK or small letter GK. We talk about the imposed load, which we call QK. Sometimes we call it life load or QK. Then we'll talk about the wind load. Wind load. This one is WK. So for this one, we're talking about the self-weight of the structure. Why this very one? We're talking about the self-weight of the structure and finishes. Then here we're talking about imposed load or life load. Considering material factors, that's the next thing we'll look at. Material factors. So based on material factors, for the purpose of durability, we need to take into account the environmental factors, where the structure will be located, and is the structure going to serve as, or is it going to, the components we are designing, is it going to serve as a substructure, or is it serving as a superstructure? So we need to put this into consideration. Then we also need to consider design strength of the material, to apply safety or consider safety measure in estimating the strength of the material. So for us to obtain the design strength of a material, we need to look at another factor called material factor, which we denote by YM. Then these factors takes into account the tolerance associated with the geometry of the structure, the variability of the material on site. We need to consider ideal construction conditions on site. Then the inconsistency in the manufacture or defects in the manufacture of the material. Then drawing condition of concrete on site, as well as degradation condition, long-term degradation condition. So we need to look at this. Because of these factors we've mentioned, we need to consider or look at the material factor of different types of materials, such as the reinforcement bar. We consider that one. The material factor for reinforcement is given by 1.15. Then for concrete, this one is given as 1.50. Then we have concrete, that's concrete in flexure or axial load. If the concrete is subjected to flexure, concrete in flexure or axial load or axial. Then the third one, this is 1, this is 2. The third one, we consider concrete in shear, under shear. We consider 1.25 as a material strength. Then for concrete or bond strength in concrete, we'll consider, we use 1.40. Then for bearing stress, which is the fifth one, consider bearing stress, this clean part of it. Talking about bearing stress, we use 1.50 as our material factor. So these are material factors which takes into account inconsistency on site and also variation on site, inconsistency during the production of these materials. So for steel, we've said is 1.15. For concrete, concrete under flexure axial 1.50, concrete under shear 1.25, bond strength in concrete 1.40, bearing strength to talk about 1.5.